Welcome back. Today we're taking toy cars and combining them with computer vision to build a real-time drift analyzer in Python. First up in the experiment is my son's favorite car, the
Cybertruck!
Yes, the Cybertruck. So we're going to do a drift analysis on the Cybertruck and see what high points we can get with the drift analysis that we build. So I put this graphic together to explain the four main steps behind generating that green heading arrow you'll see in the video. Step 1 is defining our start and end points. The computer doesn't know what the Cybertruck is, but it does know colors. We put bright red tape on the front and bright yellow tape on the back. The code uses color thresholding to find these blobs and calculates their exact center points, or centroids. The red becomes our front coordinate and the yellow becomes our back coordinate. Step 2 is creating the heading vector. Now that we have 2 points, we need to connect them to determine direction. We use a little bit of NumPy math here. By subtracting the back coordinates from the front coordinates, we create a vector. Think of it as an invisible line with a specific direction and length that tells us exactly where the nose of the car is pointing. In step 3, that is actually drawing the arrow. We want to visualize the math of the final video feed. We use OpenCV's arrowed line function. We simply tell it start drawing a yellow back point, stop at the red front point, make a green line, and give it a nice thick tip so we can easily see on the screen where it's at. And then step 4 is persistence, aka the flicker fix. When the car is moving fast or driving through shadows, the camera might lose track of the colored tape for a split second. Without this step, the green arrow would constantly flicker in and out. We added code that says if you lose track of the car for just a few frames, don't panic, just keep drawing the last known good arrow until you find the colors again. This makes sense at the final dashboard to make it look a little bit more smoother. Okay, so we just deep dived into exactly how we draw the green heading arrow. Now let's zoom out and look at the complete 4-stage pipeline for the entire drift analyzer. This graphic shows how we take the heading info and turn it into a final drift angle score. So in step 1, we're isolating the colors using HSV mask. The raw video is too complex for the computer to analyze directly. So we tell OpenCV to filter the image based on specific color ranges, in this case red and yellow. It creates these masks, which are simple black and white images. White means I found the targeted color right here, and black means ignore everything else. This cleans up the data significantly. Step 2 is finding the centroids in the heading. We just covered this in a little bit of detail, but we'll recap. We take those white blobs from the mask, find their exact center points, the centroids, and connect them to our green heading vector. This is exactly where the car's nose is pointing at any given moment. Step 3 is tracking the path to get the velocity vector. Knowing where the car is pointing is not enough. To detect a drift, we need to know where it's actually going. By saving the car's position from the previous frame and comparing it to the current position, we can draw this blue velocity vector. This arrow shows the car's true direction of travel across the floor. And step 4 is calculating the drift angle. This is where physics happen. We take the green heading vector and lay it with the blue velocity vector. If you're driving straight, these arrows overlap perfectly, but if you're sliding, they separate. We use some trigonometry, specifically the dot product, to calculate the exact angle between these two arrows. That number is our live drift angle. So let's run the code. So Here's our first attempt, which was a little buggy. You can see the red piece of tape and the yellow piece of tape that the code is using. And you can see it's following the red and the yellow pieces of tape to get aligned, but it loses it every maybe half of a rotation. So our second attempt was a success. So we were able to keep that green line between the yellow and red, and since that was happening, we could calculate our drift angle and get a speed by pixel, and we also added a little dashboard there to calculate a score, a little fake score for how good the drift was. So this is the Cyberbeast drift score here, just adding up. This is also an RC car, so we could keep it somewhat consistent on how it was drifting and the rotation it was getting. It was moving ever so slightly up after every 2 or 3 rotations. And then we decided to go do the same thing with my son's Bluey go-kart.
I'm the best drifter ever.
Yep, my son got in the driver's seat and was drifting his Bluey go-kart. So this wasn't technically a success, but the concept was shown. I put the red tape in the front and the yellow tape in the back of his go-kart, but the arrow was just tracking anything with a similar yellow or red tint, and so it was picking up the seat majority of the time and trying to connect it to that red tape in the front. And then he had red pajamas, and so the red pajamas were connecting to the yellow seat, and then sometimes the red pajamas would connect to the yellow piece of tape in the back. And so it alternated between connecting to his pajamas, the tape, his feet, and hands. So that didn't really technically work that well, but thought we'd at least give it a try. So thanks for tuning in, and hopefully you got to see something cool.